Hey there, class. We're here to look at example 2 from our dynamics notes. And to kind of start this out, basically what we're going to do here is just take a look. And this is a problem that involves both kinematics and dynamics. So you'll notice here there's our familiar kinematics picture as well as our dynamics picture known as a free body diagram. So basically what we have going on here, we have some car, and I'm going to represent it here just with the center of mass, center of gravity, and it starts at rest and it ends up having to attain 15 meters per second. Now it does this through an acceleration. That acceleration we don't know. In fact, that is what we are trying to find here in part A of this problem. So because this does involve forces, there's a rope attached to the car, and the tension may not exceed this value here. So the tension here is going to be, it's got to be less than or equal to this. Now hopefully you understand that the higher this number is, the larger the force is, the more acceleration there's going to be. So basically when we solve this out, the maximum acceleration will occur whenever the tension is at its maximum. So in our free body diagram, we do have our tension that pulls on the car. That's due to the rope that's attached to it. We have gravity, of course, that pulls downwards, as it always does. And that's due to the earth. And then the car is probably sitting on the ground, so the ground has to support it. We call that the normal force. So we have this normal force that is kind of pushing up on the car. All right, let's get down into strategy. So basically, this is a dynamics type problem, at least in the beginning, and that involves writing a net force equation. Okay, so I am going to write a net force equation. Of course, we start out with Newton's second law, and since the things that we're dealing with here are pretty much predominantly in the x direction, I'm going to mainly focus on the x direction of the motion. So here we have Newton's second law for the x direction. When we look at our forces here, we'll notice there is only one force that acts in the x direction. This is a y force, this is a y force, so these aren't important for what we're dealing with now. So the only force I have is this tension force. Since it's in the positive direction, I've put my vector direction here. Later on, some of you might like to prefer to put the positive, negative in the equation later after you substitute. I'm going to actually do it on the variable here. So this takes place of the vector nature of the variable, so therefore there is no vector anymore. It is positive. The acceleration is also positive because it's in the same direction there as well. Mathematically, I'm going to end up with the tension equaling mass times acceleration. I substitute in numbers, and after doing some algebra, I end up with the magnitude of acceleration of 2.14 meters per second squared. Now, once we know this is part A of our problem. The assumption here is that the kinematics is going to take over at this point. Basically what we have is a constant acceleration. So what we're looking for is a kinematics equation that can use this constant acceleration to find the time. I think the best option here, considering that we know the final velocity, the initial velocity, and acceleration, is probably this equation right here. Original velocity is 0. The original velocity, or sorry, final velocity is a positive. The acceleration is a positive. So when I do my algebra and solve for t, I'm going to get the final velocity divided by acceleration. Substitute in 15 meters per second and the 2.14, and I end up solving for the time of just a little over 7 seconds. Now, part C in this problem actually involves something a little bit different. Basically here, in part C of the problem, we are told that there is a resistive force. Now we're not told that it's friction, but I think it's okay to say that there's probably some kind of frictional force here. We are told that it is 250 newtons, and basically this is going to change my free body diagram a little bit. It doesn't really change my normal force, it doesn't really change my gravitational force, and it doesn't change the fact that the tension in the rope can still not exceed the it can still not exceed that 3 times 10 to the third newtons. So pretty much what I'm going to do here is kind of resolve this thing for acceleration with this new resistive force involved. So that's going to mean I'm going to need to rewrite our net force equation. So here we are, we're looking at the forces in the x direction again. So our two forces are the force of tension and the force of friction. Once I take care of the direction, again I have the direction and the magnitude in my equation. I'm putting them on the variables here. Tension was positive. Again, if we go back to our picture here, we'll notice tension is in this positive direction. The force of friction is negative, and that's going to equal mass times the positive acceleration as well. Mass times, I hope I didn't say plus there. So it's mass times the positive acceleration. Solving for acceleration, I'm going to divide by the m, and I end up with the tension minus the force of friction, and that's all divided by mass. Now, instead of putting my numbers in here, because I didn't need to actually calculate acceleration, I certainly could, but I'm not going to. I'm just going to let it go as is. What I'm next going to do is I want to reuse step 3 from before, and I'm going to substitute in my new equation. So basically, step 3 from before was that the time is equal to the final velocity divided by acceleration. Down here, I'm substituting in my new acceleration. This is the acceleration here, and you can see here with these orange parentheses around it, that has replaced what used to be an A. Do some algebra, and I'm going to actually end up with the final velocity times mass divided by the quantity ft minus ff. Substitute in the 15 meters per second. This was the mass of the car. This was the maximum tension, and this is the resistive force. I'm going to do all that math, and I end up with a time of 7.64 seconds. So to summarize, in the end, the acceleration is going to be a positive acceleration. It's going to be 2.14. The time required for to accelerate without resistive forces is this 7.01 seconds. And because there's now a resistive force, it's going to make it accelerate slower. So therefore, it is going to take me more time to accelerate to that same rate of 15 meters per second. So looks like for part C, we end up with 7.64 seconds.